So evaluating star. Star, you'll recall, is the ugly expression, which 10 minutes ago you at least agreed with me was correct, no matter what A, B, and D was. Okay? I gave you a suggested interpretation of what it means for different values of A, B, and D, so let me connect what we agree is correct upper bound with interpretations. So 1 is easy. So in case 1, if in fact the rate at which problems go up is exactly the same as the rate at which our savings and work goes down, then star is super easy to evaluate. Right? In this case, A over B to the D is 1. We raise it to the J, it's still 1. So that sum is just 1 added up log base B of n plus 1 times. Okay? And this should look super familiar from Thursday. Okay? And I can drop this leading constant in the big O, and I can ignore the log of the base in the big O. So that proves case 1 of the master method. For the other 2 cases, I have to remind you of a simple fact, which I wouldn't be surprised if it was problem number 1 on homework number 1 in a class like CS 103. So basic sums fact. So if you have a number R different than 1, R for us is going to be this ratio A over B to the D. But in general, if you have some number R different than 1, and you have some positive integer k, then the following is true. If you add up powers of R up to the k power, this is exactly the same as R to the k plus 1 over R minus 1. Okay? So I'll leave this for you to check. You can prove it by induction, or frankly, you can just multiply both sides by R minus 1 and notice that you get the same thing on both sides. Let me tell you why I'm doing this. The point of this is to make precise what we've so far been very wishy-washy about in saying that, oh, if something's getting worse every level, the last level should dominate. If something gets better every level, the top level should dominate. Okay, so this is the math which makes that justified. Okay? Yeah.
I was wondering, in the numerator on the left side, you have a microphone.
Thank you. That was a typo. Thank you. Okay? So, what's the point? The point is what I just said. Is this allows us to conclude that, you know, it's not like the top level matters the most, and then the second level matters still a little bit, and then the third level still matters, but not quite as much. Really, it says we can get rid of all the levels except the first one or the last one, depending on whether R is bigger or less than 1. Okay, that's the point. So, if R not equal to 1 is a constant, independent of everything else, as it is for us, remember A is a constant, B over D is a constant, so the ratio is a constant, then this quantity is big O of R to the K if R is greater than 1. In other words, it's dominated by the last and biggest term when R is bigger than 1. And it's O of 1 if R is less than 1. In other words, it's dominated by the first and biggest term if R is less than 1. Okay, and again, you know, if you don't believe me, I'll leave it for you to think this through in 5 minutes offline. Okay, why this fact implies this. Okay. For example, you might want to think about the special cases where R equals 2 or R equals a half. So like if R equals 2, we're doing the sum 1 plus 2 plus 4 plus 8 all the way up. So if you stop that at like 128, what you're going to get is 255. You're going to get a number which is only twice as big as the last one. So the last one is basically half of the entire sum. Okay, so in that sense, it dominates. It's big O of the sum. Similarly, if you take 1, 1/2, 1/4, 1/8, no matter how many of those numbers you add up, you're never going to get bigger than 2. Okay, so that initial term 1 is already a constant fraction, is already basically dominating the entire sum. Okay, so that's what this is saying. All right, so taking R to be the ratio of A and B to the D, first of all, for the second case, if A is less than B to D, that is, the rate of subproblem proliferation is outpaced by the rate at which the work per subproblem shrinks. So this is where the work is getting less and less as you go through the levels. Then what is star? Okay. Well, if A is less than B to the D, then this thing is less than 1. Okay? So we're in this case here. So what that basic sums fact says is that this whole sum evaluates to a constant, something that's big O of 1. So that gets multiplied by the C n to the D. So star evaluates to big O of n to the D. Okay? So that's the second case. It pains me to erase this tree at this moment, and you'll see why in a second, but so for the final case, if subproblems are proliferating even more rapidly than our savings in work per subproblem, then what does star evaluate to? Okay, so this one's a little messier. Okay, so we're evaluating star in the case where A is bigger than B to the D. So we have this C n to the D up front. And now we have to use this part of the sums fact. Okay? So the ratio is bigger than 1. The biggest and last term dominates. Okay? So what's the biggest and last term? Well, we have to plug in A over B to the D raised to the largest exponent we ever see, which is log base B of n. Okay? So let me simplify this a little bit more so it has some meaning for you. So first, here's something lucky. Let's just focus on this part, this B to the D, the reciprocal of B to the D raised to the log base B of n. So that is B to the minus D log n. Sorry, log base B of n. So let me take this D outside. So B to the log base B of n to the minus D. So what is this in here? B to the log base B of n. That is n. Right? All I've done is I've applied two operations, one of which is the inverse of the other. I started with n, I applied log base b, then I raised it to the b. Pretty stupid. I just get n back. Okay? So that's n minus d. So what have I shown you? I've shown you that this piece raised to this factor cancels that out. Leaving us with, I'm going to shove the constant c in the big O notation, leaving us with O of A to the log base B of n. Okay. Now I know you've just suffered through a sequence of a bunch of sequences of letters that didn't seem to have a lot of easy semantics. All right. I know maybe glazed over, but now wake up again just for a second. We're almost done. This sequence of letters does have some very nice semantics. And I apologize for erasing the recursion tree to make room to do the derivation. So what is the semantics of A raised to the log base B of n? Also known as what combinatorial quantity?
That's the number of leaves here.
That is the number of leaves of the tree. is that true? You start with one node at the root. Each level you get 8 times as many nodes. And remember, the depth of that tree was log base b to the n. So once you go to the bottom and collect all the leaves, how many nodes you got down there? A raised to the log base b of n power. Why is that totally expected? It's because this is the case where you do more work with each level of the recursion tree. We had our sums fact excursion, which said we're justified in saying that the largest level dominates, the largest level of the leaves. We have a constant time base case, so we do constant time per leaf. That's the number of leaves. Okay? So that's exactly what we proved. We proved that in this third case, indeed, the work of the running time, just like in the second case, up to a constant, all the work's at the top. In the third case, up to a constant, all the work's at the bottom. Okay? Constant time per leaf. This is the time at the bottom. That dominates. Of course, I'm sure you're kind of squinting and you're like, okay, but so hopefully at least this point you recognize that this, despite all the symbols, this is now something you would hope the answer would have been, given all of our intuition. This is in some sense the simplest answer we could have hoped for, conceptually. Okay, we know the work's getting worse and worse and worse. We know this is the work we do at the bottom, and in fact it dominates. That's the whole story. So conceptually, this is the right expression to think about with respect to the master method. The third case of the master method, really this is how you should think about the running time in the third case. Dominated by the leaves. Now, on the other hand, there's this other expression which from a sort of export perspective, an API perspective, is much more useful. If you just want to plug in different numbers of A and B and see what you get, as we saw with integer multiplication, this is sort of a very convenient form to work with. So this is the more operational statement of the third case of the master method. Okay, so this is the conceptually clear one. That's the more kind of useful once you're actually plugging in numbers. Now, are they really the same? It looks like they'd only be the same to kind of naive high school freshmen. Right? Because what have I done? I've taken these two things and I've just swapped the position of A and N. And I'm claiming it's the same. That never works, right? Stupid stuff like that. That never works. That can't be true. Right? Actually, but this is true. The way to prove it's true, take log base b of both sides. Right? What happens? I'm not even going to write it down. So take log base b of both sides, bring this logarithm down, and you just get on this side, you get log base b of a times log base b of n. Here you get log base b of n times log base b of a. Multiplication commutes, so those are the same number. Okay? So it looks like a naive mathematical error to just swap what's in the exponent inside the log and what's in the base, but it's actually correct. Just verify by taking logs on both sides. So in proving that the third case evaluates to the number of leaves, I have in fact proved to you that the running time in the third case of the master method is this third case here. Okay, see you Thursday.